Hello everyone. I wish you all are doing well. This is our sixth lecture in a series of 8 lectures. And today, actually, we will cover a subject, a very interesting subject that is one of the applied techniques in the hydrocarbon exploration and production, the seismic reservoir characterization. The content of our lecture today will start, as usual, by an introduction and define the reservoir characterization. This will be followed why you are using the seismic data for reservoir characterization through understanding the seismic response, the P and S with velocity theory, the reflection and transmission of normal and non-normal incident sound. This will be followed by basic rock physics. Actually, we will talk a lot about basic rock physics in this lecture. So we'll talk about how we use the AVO inversion in reservoir characterization. Also, we'll see how we use AVO for some of the attributes of the AVO inversion to identify or to detect fluids and lithology within the reservoir, in addition to using the seismic attributes for analysis. And we will have some real data examples, and we'll talk about the workflow of the quantitative reservoir characterization. So as an introduction, you know that the accurate reservoir characterization actually is a key step in developing, monitoring, and managing the reservoir and optimize the production of the reservoir. And you know the reservoir is a type of rock. We will talk in more details again about it from other sites and different than what we talked about before. But it's a container, or it's a type of rock that contains or rich in porosity and permeability that can store hydrocarbon. So the techniques that we are talking about today is seismic data interpretation, using all supporting information from seismic well tie and as we discussed before in the previous lectures, to identify the key geological markers. And if I'm working in a very complex geological area, or very complex geology area, like they have gassy chimneys, they have fractured carbonate and whatever, so I use the multi-component seismic, as we mentioned again before, and to correlate this with logging data at the drilled wells to calibrate our results and output a 3D model for the reservoir, or generally for the subsurface geology, which will be our next lecture main topic, which is reservoir model. As you know, or as a definition, the reservoir characterization is defined as a model that characterizes the reservoir based on its ability to store hydrocarbon and produce them. Doing this required actually accurate measurement, which is available from multiple sources of data or different disciplines of the geoscience, and use all this to have a quantitative representation for the reservoir. The reservoir characterization is used to indicate the reservoir fluid behavior, and under different circumstances, actually at the very beginning of the production, after salt depletion, and after injection, and so on. So to find out the optimal production techniques that are maximizing the production. There are 9 main properties to be achieved through reservoir characterization. Number one is the reservoir fault system, generally the structure of the subsurface, including or especially the reservoir, the trapping mechanism, which type of trap do we have, structures, stratigraphic, combined trap, the phase change, and the effects on the reservoir limitation, the porosity variation, hydrocarbon types and contacts, the fluid contacts, oil gas contact or oil water or gas water contacts, the limit of accumulation, how much hydrocarbon in the container or in the reservoir, and the hydrocarbon saturation, and also the volume in general. So the hydrocarbon reservoir rocks, you know that it's a type of rock, or any type of rock actually, that is characterized by the presence of porosity. And porosity, as you are familiar, is a void space within the rock. And these pores or porosity to store the commercial volumes of hydrocarbon. It also should have connective porosity, and it should have permeability. And the permeability is the fluid flow capability of the rock itself. So a good reservoir should have good porosity and good permeability in order to have production through the drill wells. What you are seeing now is a thin section from a reservoir. So let's understand the reservoir, because depending on this basis, we will cover or will understand how we characterize the reservoir using the seismic data. So what we are seeing now, again, is a thin section through a reservoir, and the reservoir, it's a rock, so it is built up of matrix, and this matrix is particles of rock, or fragments of rocks, because we are talking about sedimentary rocks or a fractured whatever type of rocks. So it contains the particles of the rocks, and this particle has type. So it could be of any different lithology or any type of lithology. Also, it has shape. Shape because it depends on the deposition. It is aeolian transported, or it is deposited in the water or whatever. So, and between this matrix, or between these rock fragments, we have the pores. And the pores contains the porosity. The porosity is a percentage, as you know, of the pores to the rock volume. And within this pores, within this porosity, there are fluids. So which type of fluids are there? Does these fluids air, gas, or oil? So the reservoir rock is formed of the matrix and pores. And the overall rock properties is determined, the rock, I mean here the reservoir rock, are determined by the matrix type, the porosity, and the fluid. And the reservoir has a bulk density. So, and the bulk density can be calculated from the equation that you see here. So the bulk, this equation contains the density of the matrix, the porosity, the density of the water saturation, the hydrocarbon saturation, and the water saturation again, as I just mentioned. So everything in the reservoir is governed by equations, and from this we will characterize each reservoir. Why do we use seismic for reservoir characterization? So you know that we have different benefits of the seismic. The simplest one of these is that seismic covers a huge area. Okay, so let's see why we use seismic. So to answer this question, we have to answer another question. What causes a seismic response? Okay, how can I have a seismic response? As we mentioned before, the changes in bulk rock velocity or density, when I have two successive rock units, two successive different rock units, each one of them will have its own density and on velocity. And we mentioned before that this velocity is the sound wave propagation velocity within each. So what causes a seismic response is the change in bulk rock velocity or density, or both together. So the lithology is one of the reasons. So the lithology means that what type of rocks do I have? We have sandstone, shale, for example, limestone, or salt. So suppose you use a hammer and you use this hammer to take a shale. What type of sound you will hear? Does it equal to that when you hit a limestone? It's different. Why I get these differences? Because of the difference in density between the shale and limestone, and also the difference in the velocity of sound propagation within each type of rock. Okay, so it is coming from this very simple basis. So let's continue and see how the seismic response, or from where the seismic response came. So we mentioned that the change in bulk rock velocity or density, and the lithology is one of the reasons. The second one is the porosity. Okay, and the porosity is a percentage of the pore space within the rock, and we have different types of porosity as you were familiar. So this porosity could be primary porosity or secondary porosity, and it depends on the porosity of the rock, the velocity of the sound wave will be changed. So if you have compacted rock, as you see, for example, here, so if you have like a compacted rock like this one, so the sound will travel fast or faster than if you have a less compacted rock like this, because for this compacted rock, the density is high, because the porosity is low, okay, comparing to this type. So sorting of the reservoir itself is a matter. So the porosity is a matter of the seismic response that we measure. So this is add to the seismic method importance, that it's sensitive. So what I mean, the responses that I measured from the seismic reflection method, it comes from a lot of petrophysical parameters of the reservoir itself, such as the density, the velocity, and the lithology, and the porosity. So I can know each constituent alone. When we finish, let's see more. What's more? Give me the seismic response. So after that, you have the mineralogy, or the fluid type itself. So the mineralogy is different than the lithology. Lithology is what I'm describing the rock, the type of rock itself. But if I have a sandstone rock, sand is the size, it's not the mineral. Okay, but it could be, the sandstone rock could be built up of quartz, could be built up of feldspar, could be built up of carbonate, whatever. But if these are the mineralogy, and the mineralogy in all cases that I just mentioned has the same size. So the mineralogy also affects that. So calcite gives me seismic response different than dolomite, different than the other carbonaceous and shales. The fluid type also different. So if the sound velocity is changing from traveling through water or gas or oil, it is different. So you have, if you check this table here, you'll find if I have a sandstone with 30% porosity, when it is full, the pores are full of salt water, the density will be this number. And it will be decreased if this is the fresh water, and it will be whatever decrease in the oil and the gas. So we mentioned that one of the responses is the velocity, and it depends on what we were talking about before. So let's understand the velocity theory. What type of velocity, how the wave propagates, the sound wave propagates within the rock. But from other side, we talk about this in the previous lectures. But the point is, if you remember how the sound wave travels from the source towards the subsurface, we mentioned that this is through the rock, because we try to understand the subsurface structure and stratigraphy. And we mentioned that the particles of the rock oscillate. Okay, and this oscillation is a type of deformation. And this deformation is elastic deformation. You never hear that we acquire seismic in some place and it broke, or the structure changes, or it get faulted, or whatever. So this deformation is elastic because the particles oscillate until the energy travels from this place and it returns to its original position. So if you take a look on this cartoon, so if this is the start of one of the particles, and then you have like a shear deformation for it, when sound energy done, it returns back to its original shape. Because of that, it's an elastic deformation. Suppose you have like a plastic ruler. If you push it like this and lift it, it will return back to its shape. But if you press more, you will get a plastic deformation. The plastic deformation is that this ruler will not return back to its original shape. And this is what happened in folding, for example. So in folding, in geological folding or rock folding, this is what happens. This is what we call the plastic deformation, because what I mean, there was a tectonic forces that push these rocks and it get folded, but it will never get back to its origin. So this is what we call plastic deformation. If this force acts more than that, yes, it will get broken, and then we'll get fracture point and we'll get the faults within the rock. So again, as I just mentioned, when you acquire seismic data, the ground stays as it is before and after the seismic experiment of the seismic acquisition. So because of that, it's an elastic deformation. So what we're talking about is elastic deformation. Okay. So let's continue and see what type of that. Hook is a scientist that he mentioned that the force you exerted on this tube, for example, to change its shape, it's called the stress. Okay, and this deformation is called the strain. The changing in shape is called the strain. Okay, and he mentioned that the stress is proportional to the strain. And if I want to change this proportional sign with an equal sign, as you all know, we should have a constant in the equation. So stress is equal constant by strain. This constant will be called the K in case of the compression. So if this formation was a compression like this one, so the constant will call the K and we call it the bulk modulus. Another shape of deformation, which is the elongation. If the particle get elongated, okay, so the constant will be called the E, or the Young's modulus, which we give it the sign of E. So this in case of the elastic deformation or elastic elongation. And the last or the third type of elastic deformation is the shear deformation, and the constant here will call the mu. So, and this is called the shear modulus. So we have the elastic moduli. The elastic moduli, what are the elastic moduli? These are the constants of the Hooke's law, stress proportional to the strain, and this is the constant in case of each one of these three deformations. So what I'm gonna use this for? Yeah, this is a deformation happened within the rock when the sound wave enter this rock and propagate on this rock with certain velocity. Okay, so using this elastic moduli, I can calculate the sound velocity within target. So and we mentioned that I have primary waves and I have shear waves, if you remember from the previous lectures. So the velocity of the P wave is equal to the square root of the bulk modulus plus 4/3 shear modulus over density. And the shear wave velocity can calculate it as you see a square root of the shear modulus over the density. Or we have a different other, expressions. The most important thing, because we will talk about this in splitting reservoir characterization parameters, is lambda and mu, which are called the Lame coefficients or the Lame parameters. So please concentrate on this to know that I have elastic moduli and I have the Lame constants or the Lame coefficients that we will use each one of them to characterize the reservoir. Why? Because each one of them give me the response, is a reason of the response of the seismic data that I pick up. So let's go further and understand how the incident energy from the seismic source will reflect and refract with the presence of in the subsurface generally speaking. So I have two different ways. The first one, which is what I mean more or less is not what happened in the reality, is if I have like this is an interface between two successive group units, and I have the P wave incident from the source of energy, it will hit this boundary between two different group units again, and part of it will be reflected back, but perpendicularly on this interface, and part will be refracted down again as straight. So each rock unit will have its own P wave velocity and the density. Okay, and as you remember that for the wave that hits a boundary at normal incident angle or normal incident, the expression of the reflection coefficient is the reflection coefficient equal the acoustic impedance of the lower layer minus the acoustic impedance of the upper layer over their addition. In reality, what happened is that when the source of energy emits the sound, the energy goes everywhere, so it incident on this interface with different angles. So if I have this interface now, and I have, this is the incident P energy, P means P wave energy. At this interface, part of it will refract or penetrate deeper to the next layer as P. And I will let you know why I call it PP now. So it is refract as P wave. Because of that, we give it the letter PP. PP means that incident as P and refracted as P. And another part will reflect back to the surface. And it is PP reflected. And PP reflected because it was incident as P and reflected as P. But because of this angle, a criteria called mode inversion happened in this. So part of the incident energy will reflect as shear wave, not P, will reflect as shear wave. And part will be refracted as shear wave. Because of that, we call it PS reflected. So it was incident as B and reflected as S. And PS transmitted, which means that it was incident as B, but transmitted or refracted as is. So this is what we call the mode conversion between the B and S wave. S wave, yes, also can be converted back to B wave. So a scientist called Zobrits, he drove 4 equations actually, and here is the key point that these 4 equations determine the amplitude reflected and refracted waves as a function of angle of incidence. So if I know the angle of incidence, I can calculate the amplitude of the data that will be reflected. The reflection and transmission coefficient with angle of incidence, this is used to know the fluid content of the rocks. And the technique that we use for that is called the AVO, or the amplitude variation with offset. And this is the main key for the reservoir characterization actually using the seismic data. So the practical use of the non-normal incident phenomena known as AVO or AVA, amplitude variation with offset, or amplitude variation with angle. And as Zopritz had 4 equations, the science came after that to start to simplify these 4 equations until we reached to a scientist called Shoei, and he made an approximation and ended up with this very famous equation, okay, that we'll understand it very well in the coming slide. So the R naught is a reflection coefficient at the 0 offset, which is the normal incident. Okay. G is called the AVO gradient, which is describing the reflection behavior at intermediate offsets. Theta is the angle of incidence. Okay. And this equation, we will see how much we use it to identify the lithology and fluid within the reservoir. So let's see how we characterize the seismic reservoir using the AVO. A scientist called William Ostrander published a paper, and he mentioned in this paper that the offset dependence reflectivity will give me a clue about the fluid content within the reservoir. So if I have a seismic section, this is a normal seismic section, vertical seismic section. This reflector here is the target, and as you know, this axis is two-way time, and this axis is a CDP location. And if I choose a CMP location that hits this reservoir with this target zone, I can get back to the pre-stack, because this is a stack section. And if you remember the processing, we have a pre-stack processing. So I can return back to the pre-stack and extract the CMP gather, or the CDB gather, and follow up the amplitude from the near offset to the far offset and check, does it change or not? So he showed that if I have a gas saturated sand capped within shale, or capped by a shale, this would cause an amplitude variation with offset, as you see. So if my amplitude was at the negative 0.05, and if I move the far offset, it will increase. This is what you see here. You start with a blue color and go to a yellow color. The yellow color here means that it's of higher amplitude. Okay. Also, when the AVO technology became a commercial tool in the industry, it was used to find the relation between the amplitude and properties, and from just the seismic and apply AVO analysis, and then see what AVO class do you have, we will reach to the lithology and the fluid within it. So you have here a shale overlie sandstone with gas. So this is a gas, and this is the response, and start from what I mean the seismic and reach to the lithology and the fluid content. So why AVO is working for reservoir characterization? This just remind you with the reservoir section. So the AVO goal, so applying the AVO is amplitude variation with offset, or AVA amplitude variation with angle. The goal of this method is to determine the density of the reservoir, the B wave velocity from the equations you know, the S wave velocity, the Poisson ratio. What's the Poisson ratio? It is derived from the VP and VS, or the shear and P velocities. And then when we calculate this or estimate this using the AVO method applied on seismic data, we will end up with identifying the lithology and the fluid from all these parameters. And this comes from different relations, different physical relations, like the density, like the water saturation against density, like the porosity when I plotted against the Poisson ratio, or I'm sorry, the velocity relationship, the porosity against velocity. I can identify where is my, what I mean, lithology and so on. Also, when we plot Poisson ratio against the VP VS ratio, and you remember, and this is a equation for the Poisson ratio. Poisson ratio got the letter of sigma. So this is totally fine, but I mean, we use very simple parameters, physical parameters from the reservoir that reflects on the seismic data and return back to what I mean to the subsurface rocks. And how about the fluid content and the lithology. So simply, the AVO depends on the angle of incidence. So if you have these cartoons that represent a CMP, here this is a CMP point, and you have several sources, and this energy reflected back to different receivers that all cover the same subsurface point. If you count here, you have about 3 rays. So when we plot this CMP gather, we will have the amplitude. This is a corrected. If you remember the processing, an NMO corrected CMP gather. So you can see the traces for each of this one, and you can follow up the amplitude here. Okay, so this is the basics of the AVO. We follow up the amplitude across the offsets and see if does it change or not. So, and we use cross plots. So according to this equation of showing, okay, we can plot the sine square theta, which theta is the angle of incidence, okay, and this is a gradient. If we plot the sine theta against the amplitude, from where you get the amplitude? From here, okay, and then I can take the best fit. The slope here is a gradient, which is the G, and if you and this is the R naught, or the what we call the intercept. Going further, so what happened after that? We can plot this P naught or R naught against the gradient, and if I plot them against each other, I can locate from the amplitude my data in it, and this data will represent the lithology, shale, sand, gas sand, whatever. And then from this cross plot, I can identify the type of rocks in my seismic data. So I start from seismic data, and I return back after the calculations to the seismic data, and splice on it or plot on it the reservoir and the type of lithology on this seismic. This is simply what happened. So going further with this cross plotting, so the rock physics diagnostics can be done from cross plotting or plotting graphically the VS, the velocity of the shear wave, versus porosity, for example. So I can plot the porosity against the VS, for example, and this is showed what we've seen here is a shear wave velocity log data versus total porosity, and there is a superposition of the diagnostic rock physics model. So using the model, we can quantify the cement volume, we can quantify the degree of sorting of the data, we can, what I mean, see the lithology, like the shades that we see here, and see the effect of the gamma rays that was read in the windows. Again, also I can understand the positional environment. Okay, like here we or in this paper we have the gamma ray log in this axis, and we have the acoustic impedance in this axis. You know the acoustic impedance is rho by V, and this is the acoustic impedance versus VPVS, and this is acoustic impedance, and here is, and this plot is the VPVS, and both are plotted against the gamma ray. So you can interpret what I mean. Each color represents a lithology. So, for example, what you have seen in these plots is a clean sand and shales have similar acoustic impedance values, and the shaly interpreted sand have a relatively high impedance value. So we can interpret that, and all of this comes from the seismic using the AVO method. So let's see more from this cross-plotting to understand. So we will add one more, application that a scientist called Gassman used to add to the AVO in relation to the rock physics. Which is the seismic fluid sensitivity, and this is theory is called Gassman theory, actually using his name, and this is used for fluid substitution. So the seismic fluid sensitivity is determined by the combination of porosity and pore space stiffness. A soft rock will have a larger sensitivity to fluid than the stiffer, if both have the same porosity. So let's understand that. So we can, and he generates what I mean, a rock physics template. So when you can plot the acoustic impedance against the VPVS ratio, you see how this ratio is very important in the AVO inversion on the usage of AVO. Then you can differentiate between different lithology, like the shale. This is the shale, for example. This is a brine sand filled with brine or salt water, and this is the oil sand. So you can find them in different places. Also, the water circulation decreasing in this direction, and so on. This is the matter of interpretation, and all based on very simple parameters, and you understand now from where we get this parameter, because these parameters are causing the seismic response, and we going the other way. From the seismic response, we start to invert to understand these simple petrophysical parameters. So this is what we call again the rock physics template. So we can combine the depositional and diagenetic trend models with the Gassman fluid distribution and make charts or templates of rock physics models. So if you take a look here, this is a rock physics template, and you can see where here it is the acoustic impedance on the x-axis against the VPVS, and you can see different clusters, and each cluster represents a type of rock. For example, one is a cap rock, and you can see that two is a prime reservoir, and so on. So you can differentiate between this, and as I told you before, and we will see again, that we can use this block. So we start from seismic again, and we have our cross plots. What I mean here, between the Poisson reflectivity and the normal incident, the R0, and you can differentiate between the different sands, gas sands, brine sands, oil sand, whatever, and the shale where this is found, and you can post that on the vertical seismic section, so you can know where is your reservoir, which is in red color. This is a well. This is the reservoir, gas reservoir, and here's also you have the lithologies here, and so on this seismic you post the lithology and fluid content of this seismic. So let's see furthermore. So if I have, for example, the seismic data, and I split the seismic volume into the near stack and the far stack and the gradient these are attributes from the seismic data. So what I mean, near stack means that I apply the stacking processing process on only the near offset traces. Far stack means that I took the far offset traces and stacked them. And you can see here we have two wells, and you can follow up what I mean, this anomalous amplitude, which indicates the presence of hydrocarbon. Okay, so this is on this seismic data or vertical seismic section. You start to do your cross plots that we're talking about, and the AVO cross plots, and you start to identify the fluid contents and the lithology. Again, I repeat what I showed you before, but just to understand it well. So I will end up with, this is the delta VSVP, which shows the cement, so the non-porous rocks, and they are away from the wells. And this one is the fluid factor, and you have the fluid are concentrated around. Okay, so fluids, because this is a gas ones. So this is how we use this reservoir characterization and see using the AVO to understand the lithology and fluid. So to summarize what we're talking about, we mentioned something about the AVO inversion. And in AVO inversion, we take the seismic data, remember, in the pre-stack domain, before stacking the data. Okay? Because this is represent the reflection coefficient of the data as a function of angle of incidence. And we use the Socrates equations. We try to convert this data back to reflectivity. What is the reflectivity? Yes, it is a reflection coefficient, and back to the acoustic impedance. And the acoustic impedance is rho by V, so I can convert into the rho and the. So the reflectivity means that the change in the rock parameters, like the relative change in the P wave velocity, so delta Vp over Vp, and the relative change in shear wave velocity and the density. So I can get this from this inversion. This is what we had in the previous slides. And then to perform the inversion, the AVO inversion, we need to know the angle of incidence of all gathers. The gathers means the CMB gathers, and the offsets, the different offsets, and the time and or depth samples. This is from the seismic data itself. So I need to know the angle. So how can I get these angles? As I just showed you in the previous slide, I can take the near offsets, and the near offsets are related to the near angles of incidence, and the far offsets that are more or less related to the far angle incidence. And then if I have a good velocity model from the source to the receiver location, I can understand how the ray, what I mean, reflected back from the subsurface. This is the output of some of the inversion, like this is the full stack. Full stack is a normal seismic data, okay? And then from the inversion, I can get the near angle stack, the far angle stack, I can have the P wave reflectivity, I can have the fluid stack, as you see the gas magnitude. So, and this is what we call also attributes, because I extracted all these four, 1, 2, 3, 4, from this one. So this, all of these are included in the full stack. The full stack is the normal stack on the normal use of the seismic data. But I can get these attributes to estimate the physical parameter, those rock physics parameters that we were talking from the beginning of the lecture. So let's see more advanced application for the reservoir characterization using the AVO technique, which is using the lambda and mu. And you remember these two equations when we're talking about the principles at the very beginning. So I have the lambda here, and I have the mu here, and we call these the Lame parameters, or the Lame constants. So the Lame parameters are the mu, which we call the rigidity, and the lambda, which we call the incompressibility, or what I mean represents the incompressibility. Mu represents the rigidity of the reservoir. Lambda represents the incompressibility of the reservoir. So and then we extract two attributes which are newly applied in the industry. One of them is called lambda rho attribute, and the other is called the mu rho attribute. What are the importance of this application or of these new attributes? Actually, this is used to improve the identification of the reservoir poor flow. How? Because a better understanding of lithological variation can be obtained by analyzing the changes in mu and rho and lambda and the rho parameters within the seismic velocity or impedance. So if I analyze all of these ones, we will understand the differences or the variations within the flow, the reservoir fluid, and we'll see applied examples to understand that. So let's see a real data example that the authors, you can find what I mean, you can find this paper in the first break, volume 34, and so on. So the authors of this published paper, what I mean, try to characterize an unconventional reservoir. So the unconventional reservoir means that you think different about the reservoir type itself. So let's see what happened. So for successful exploitation of unconventional reservoirs, it has been proved necessary to differentiate the more brittle from ductile rocks to maximize reservoir recovery. Okay, because the brittle rock, you can what I mean, fracture it more than the ductile. Okay, so the economic gas production in this sort of unconventional place requires hydraulic fracture stimulation, and the hydraulic fracture stimulation will work much better in the brittle rock than the ductile. Okay, so they want to identify within this unconventional reservoir rock type or reservoir type, where are the brittle zones to use the hydraulic fracturing stimulation to enhance the production of the reservoir. So they utilizes the impedance, what's the impedance? Acoustic impedance, density by velocity, the density, and the Lame parameter for Lame constant, and they extracted the attributes of lambda rho, and mu rho looks, okay, and they drove this, and using, of course, the amplitude variation of offset, they do the inversion of the AVO to extract the mu and the lambda and rho. Okay, and they use this with, again, the Poisson ratio to identify where are the brittle parts of the reservoir. So let's continue and see what happens. So we started from seismic data, and the seismic data has the interpretation. Where are my formations and where are my reservoir, or where is my reservoir, and what are the ages, and so on. So it's the normal interpretation, conventional interpretation on the seismic data. This is followed by the checking or doing like a visibility study to see the theories, what the theories said about the relation between the lambda rho and the mu rho. So the theoretical, what I mean, basis mentions that if you have the lambda rho in this axis and the mu rho in this axis, you will find the carbonate rock in this part, and you'll find the shale in this part, and the tight gas rock, which is unconventional reservoir, in this part. And plotting the curves between the Poisson ratio and Young's modulus. You remember Young's modulus? The constant, yes, of the elongation of elastic deformation. And they can also know that you will have here the ductile region, and in this area you'll have the brittle region, and the brittleability is increasing in this direction. So this is a theory. Okay, then they use this relationship and apply it on the inverted parameters that they got output from the AVO seismic data, and they have this linear regression analysis to find out the relation between the Poisson ratio, okay, and the Young's modulus from the real data, from the seismic data. And this is how it looks. Followed that they know now the relation between the seismic traces and seismic reflectivity and the brittleness. So they converted the whole seismic cube into a whole brittleness volume. And this color bar indicate where are the brittle and where are the ductiles. So you know now where you can, apply the function. Okay, so going to another example, or continue with this one. So they start to, after that, to plot or cross-plot the lambda mu rho attribute. So you have here, they have here the Poisson ratio against the Young's modulus, and they have here the lambda rho against the mu rho. Okay, and in each one, in this one you have the curves of the brittleness. So they know where is the sandstone interval. Okay, and here is you know where is the carbonate and where are the sand and where are the quartz, where are the oil or the clay. I'm sorry. So from cross plotting. So this is they found, and they had a visibility study at the start, and they have the theoretical relationship, and they took this relation and applied it on the data. And and by the end, they had the geobodies for the reservoirs. You understand where is the reservoir, okay, from the mu rho section, okay, and the lambda rho section. So these are the cross-sectional view, highlighting the reservoir interval within the lambda rho and mu rho. One of them indicates the lithology, and the other indicates the fluid, content. So let's see another example, which is seismic attributes, not the AVO inversion. They were using in this publication, and this is the link for this publication. They use a seismic attribute analysis for reservoir characterization. So they use seismic attributes because it is important qualitative and quantitative predictors for reservoir properties and geometries when you correct that or used for reservoir characterization. So the seismic attribute reveal information which are not readily apparent in the normal seismic, or the raw seismic data. Why? They identify the reservoir, they delineate the bay zone, and they determine the distribution of the relevant properties such as thickness, porosity, and lithology. So let's see what they did. So this is the input seismic data. This is a normal seismic section, okay, two-way time, and here is CMP. Okay, so this is the reservoir is in this highlighted area. So they extracted the instantaneous amplitude attribute, and you have here in seismic section, this is attribute in seismic section, and they extracted on horizontal slices, and this is how the absolute and instantaneous amplitude attribute distributed horizontally. After that, they got the porosity from some logs they have in the area, and they started to cross-plot porosity against the instantaneous amplitude. So they have the instantaneous amplitude in this axis, and this is the porosity. And they cross-plot here the porosity versus an attribute called the quality factor, or the quality factor, to understand which attributes give them the better results. And they got the distribution of the porosity when they found the relation from this one on using these attributes. They have the distribution of the porosity on the instantaneous amplitude and the quality factor, as you see. So you have the color bar, high porosity is there, in the red, so you know now in your area where are the higher porosity reservoirs. So generally speaking, summarize what we have said is starting from normal 3D seismic, and then You can invert that using AVO or whatever, using some log data, like the gamma ray. You can have a gamma ray cube. You can have the lambda rho attribute cube. You have the mu rho attribute cube. Okay. And also you can get the brittleness index from the seismic. You can use attributes to know the subsurface structure and the distribution of your lithology. You can end up with a cube of the porosity distribution from your data, even the permeability within your reservoirs. So to summarize this and to understand the workflow, at the beginning, you acquire seismic data. Then you process seismic data, because seismic acquisition and processing providing the most appropriate data for the reservoir characterization. After that, you do structural interpretation and stratigraphic interpretation. Because structural interpretation providing the shape of the reservoir, and stratigraphic interpretation delineating the phases change. This is followed by quantitative interpretation, in which you get the rock physics parameters or the elastic parameters, like the velocity of the V waves, the velocity of shear waves, the density, and this is from the physical parameter from logs, and you convert that or invert that from the seismic data itself, and you can get more attributes and AVO attributes, and so on, and then you determine the productivity or you use your reservoir simulation. For more or more detailed workflow, you generate a rock property, volume, and the maps from seismic data. Then you characterize or using the either pre-stack analysis, full stack analysis, deterministic inversion, any type of inversion. Then you predict the property distribution using the neural network, which is the subject of our last lecture. You can use neural networks, the numerical models, with more confident, what I mean, rating. You can use extend your application to the AVO domain to obtain the fluid as we talk, and can work in a very complex area, if it has heavy oil or so on, and then you pick the technique. You must suit it for your geological setting of the area, and you can analyze and characterize your reservoir. With this slide, I conclude my presentation, and I will be happy to answer your questions, if any.